Okay, thank you very much, Robert. My name is Danny Puthawala. I'm from Nationwide Children's Hospital in Columbus, Ohio, in the city, in the country we don't talk about. But I know this is the last stop before caffeine, so I'm going to try and keep it quick, short, intuitive, and hopefully even kind of fun. I want to come to you to talk to you today about a new data standard from GA4GH and about a problem that you may not even have realized you've been grappling with, or that folks that you rely on have been grappling with, and what we're doing about that to fix it. So today we're going to talk about categorical variants and the problems they cause. Categorical variants I'm going to call Cat-VRS. That's one of the two words I'm going to make up for today. The second one is how the categorical variation representation specification Cat-VRS solves those and what that does for you. So first, the problems with Cat-VRS. So what is a Cat-VAR anyway, right? I work in a hospital. A problem that we often are asking ourselves when we're looking at genomics cases is this a variant that we've seen already? And more often, is this a variant that we can match to another one we've seen already, even if they're a little bit different, right? They might not be exactly the same, but they're in the same group for some useful purpose of that term. And so when you are referring to an entire group of variants at once, this is what has come to be called a categorical variant. So a Cat-VAR is just a group of genomic variants of some useful class. Here's some examples of ones you may or may not have heard about, things like BRAF V600E, depending on the transcript you're working on, depending on the reference genome you're working from, right? There's an entire set there that you might be referring to. EGFR gain of function, a little more open-ended of one. TP53 loss, who knows why it's gone? Maybe it got deleted, maybe it got turned off. There's many ways you can get lost of TP53. One you might not have heard about, MET delta X14, which is for MET exon 14 skipping mutations. So here's why these are problematic, okay? Cat-VARs like MEX delta F14 are core to variant interpretation because they are used in knowledge bases to link real-world variants to the knowledge we have about them, whether that's phenotypes they're associated with, therapeutic indications, annotations, evidence items, etc. When people were building our first generation of knowledge bases, often these times these were just string labels that were human readable that we stuck on there to make sense to our human annotators. And the problem is that they're just labels, string labels that make sense to human annotators and not to our computers. So there's some fundamental real-world representation problems that we're trying to solve here, or at least provide a starting solution for. So why aren't these things computable? Why do we need a standard to work on this? Well, let's take our MET delta X14, which, as I said before, is for exon skipping mutations specifically. And there's a number of problems that make this hard for computers to deal with. First of all, delta, what's that doing there? That's not part of any standard nomenclature. And usually when people use delta, they're using some change here, not specifically exon skipping mutations, which is kind of weird. Matching down to a genomic coordinate might be non-trivial, especially if it's from an intronic region, like a donor acceptor site variant or something like that. Alignment might be weird. So this is most transcripts, this might be exon 14, but on this particular transcript, it's exon 13. Having to compute that over is not trivial. Also, trying to relate this to other variants of interest. Turns out that exon skipping in this particular domain makes the protein more active. So it's a gain of function type variant. So that you might also be interested in, they had this or something like MET amplification in terms of clinical outcomes. So all these kinds of challenges make it very hard to compute efficiently and do useful things with this genomic knowledge. And also is a nightmare for curation if you're running one of these knowledge bases. So we might turn to and say, okay, what can we use to represent these Cat-VARs in a more efficient way? There are a couple of things we tried as a field over the time, but there were no really good solutions. So if you try to use something bottom up, like Speedy, for example, which does work for canonical alleles, but only for canonical alleles, right? The scope of those is really narrow because they just weren't built to handle categorical variation at a broad scale. On the other hand, if you want to go top down, use something like, okay, let's just all use the HGVS nomenclature. We can be cool. Unfortunately, when you tend to specify these top-down nomenclatures, they tend to have gaps. They're too inflexible. They don't accurately reflect what the humans are talking about when we're making up these categories. So we had to come up with a solution. But finally, something we're all interested in as computationalists, extensional modeling doesn't scale. And what I mean by extensional modeling is if you have a set and you say, it's the set with these members. Yeah. This is what we did when we started building knowledge bases. So this is an example from Civic where they have a particular variant and they have, here's the list of members of that variant class. Yeah. This is difficult and inefficient to curate. It's a nightmare if you have to hand annotate these things. And it just simply does not scale. So for an example, let's say we're talking about EGFR exon 19 sequence variants. And I'm going to tie one hand behind my back and say we're only going to talk about the length neutral ones. So no net insertions, no net deletions, just like del-ins or substitutions, yeah? There's approximately 10 to the 125 of those. So that's a big number, but how big of a number is it? There's an upper estimate for the number of atoms in the universe is about 10 to the 80. So if we pretend that that number is this circle, and we use our imagination here, we pretend that that circle is 1 centimeter in diameter, then the circle of the EGFR exon 19 sequence variants is definitely not to scale. If this were to scale, it would be, by my math, the size of the Milky Way galaxy. So you just can't construct these sets. You can't query them efficiently. We need a better way to do this. So we got set this problem by G4J. We sat down to try and figure out how we can handle these computably in a more efficient manner that works for more people. And so we set about herding our cats. And we started by reframing the problem. People come up with these labels to represent these classes of variants. What are they trying to say? Like, what do they mean when they come up with these labels? And let's try and represent that. So the answer turned out to be, and this was fortunate that my background's kind of in natural language semantics, a relatively small number of fairly common and recurring properties. Things like where the variant's taking place, if there's a copy number change involved, if there's a function change, if translocation has happened, things like this. And importantly, keep this in the back of your mind for later, these can be extremely vague or extremely precise, right? One particular SNV in one particular part of the genome, that's extremely specific. Or we could be talking about chromosome 7 variants, which is extremely vague. So instead of being extensional, we went the other way. We made an intentional model, and in fact, a hyperintensional model. Now, for the purpose of this talk, hyperintentionality is a little bit beyond what maybe is worth going into, but happy to talk about that over wine. But an intentional set definition is, instead of saying it's the set of these members, we say it's the set of things with these properties that are common to all the members. The basic idea of hyperintentionality is, by the way, we can have two things with all the same properties, but give them different names and we'll keep them separate. So if you have an example of like an HGVS expression from the oncogenicity literature versus a star allele from the PGX literature that happen to have all the same properties under the surface, right? Those are useful to keep separate for those kinds of reasons. So once we figure out a intentional model semantics for categorical variants, all we need to do then is make sure that our properties, or what we call constraints, are computable, and we're golden. So in Cat-VRS, Cat-VRs aren't labels. What they are constraints on set membership. So our example over here before of MET delta X14 is really telling us three things. One, we're talking about variants that are in the region of MET, exon 14. Two, that they involve exon skipping as a protein consequence. And three, if you care about that part for the clinical part, that it's a gain of function type variant, right? And the set union of those is our thing we care about. So importantly, these constraints are explicit. They mean exactly what they say. And we can be very precise with that. They're computable. We can make these things that computers can understand and work with. And they're human aligned. And by that, what I mean is the properties that we chose and how we decide to represent them are intended to align with people's intuition of what they mean when they're coming up with these labels. So that A, hopefully people actually use the system, and B, so that they're less likely to misuse it due to having unintuitive parts once they sort of figure out how it works. Now, getting back to the specificity and vagueness part, some categorical variants are fairly specific, like BREF V600E, which is why you may have raised an eyebrow when I first said that. Others are a lot more less specific and more vague, like TP53 loss, right? There's a lot of ways you can lose that function of that gene or get deleted. And Cat-VRS handles both without introducing over precision or damaging data provenance by breaking those different dimensions of meaning out and then modeling those separately and the specificity of those properties separately. So what's the payoff on this? Well, first of all, it allows us to start searching this kind of data in ways that we just typically haven't been able to do in lots of different resources in really cool ways. So we want to check, hey, how closely related are these two Cat-VRS, these two groups of variants? We can do this by breaking out the constraints individually and comparing those. So we take a relatively well understood class of problem, constraint satisfaction problems. We break that down into a series of simpler problems, and then it's a lot more efficient to do all the matching. So in this case, you can see like on your left, right, we have, these are both in the BRCA1 variants, the regions BRCA1. Someone has said, oh, that's a gene, by the way, and they could point to an ontology they care about, either ensemble or HNC or whatever, to tell us what exactly they mean by that gene, right? And in this case, both of those are identical. So we know we have a match in the location dimension. The guy on the left, we're talking about something with exactly 4 copies in the genome for some reason. On the other case, we have a range of 3 to 7. So we now can make an inference about the fact that the variant on the left class is a subset of the variant on the right class, which is a predictory example in this case, but this kind of matching and search is something that you just couldn't do before programmatically, which was awesome. So Cat-VRS, we've also done a lot of work to make sure that Cat-VRS is fair as we can make it. It's findable. This kind of search that I've been alluding to by constraint, because they're structured entities, enables entirely new search strategies, which have been very helpful for the people that have started adopting it so far, both for knowledge producers and curating their own knowledge bases, as well as knowledge consumers who want to find information on the variants. It's accessible. I can't do anything about the data. If other people have the data and that's proprietary, well, that's them. But all of our documentation, our implementations is available on GitHub. We have an open source MIT license on that. You can take it, you can plake it, you can fork it, you can do whatever you want. It's all on GitHub, and you can find it there. It's interoperable. One of the goals of this system, of this new data standard, is to allow various implementers, both on the knowledge producer side and the knowledge consumer side, to be able to have a common language for talking about categorical variants with each other, with the aim of reducing the barriers to interoperability across the field. And finally, it makes the data more reusable by enabling harmonized representations across knowledge bases for curation, integration, and reanalysis. So how am I doing on time, by the way? Great. Awesome. So in sum, Cat-VRS provides a Cat-VRS semantics that computers can use, which is a win. We support the precision or imprecision of human expression and meet them where we're at, so as we don't damage provenance and we don't introduce over precision. We address an open problem in variant representation. We enable novel strategies for Cat-VRS search and curation, and we bring new efficiencies to research and clinical genomics workflows. So this is the part where I tell you, by the way, it's out now. So please help us share the future of fair genomic knowledge. Cat-VRS was released this year by GA4GH, and it's now part and interoperable with the other standards in the GA4GH ecosystem, some of which you may have heard of, like VCF, some of which you may have not have heard of, like Verse or VA-Spec, which is pretty new, and Beacon and stuff like this. We've also been partnering with a lot of, mostly on the knowledge producer side at the moment, folks to get adoption of this out and see what it can do for them. It's live on a version of ClinVar that uses the GKS standards. MaveDB is running on this. Civic is slated to update a lot of their internal models to make it compatible with Cat-VRS. The Vic MetaKB is running this, and many more. So hopefully Cat-VRS will be coming to a knowledge base near you and be helpful for you for now. So with that, I'd just like to thank all the folks that have helped us with it from across the globe. We're getting this started, figured out, and made available for you. On the left side, my lab from the Wagner Lab at Children's, Brendan, my co-author and co-lead of the development group there, and Beatrice from GA4GH, who we couldn't have done any of this without. So with that, I hope to see you in the Cat-VRS. Check out the QR code for all of our documentation and code, and let me know if you have questions.
Very nice. We still have time for some questions. So since you're at Dana-Farber, like, would this be used for the onco panel and all the patients that are coming in?
Okay, so Brendan, my co-author, is at the Dana-Farber, but they are planning to use this within their involvement with MOA, and I'm not specific. The Molecular Ontology Almanac. It's a knowledge base that they run, that he's involved with. I don't know to the extent to which he's implementing it in the clinical side there, although I do have onboarded a couple of their developers, so I think they have some things in the works. At Children's, we have a number of computational pipelines that we currently run that are, some of which have integrated earlier versions of this work as we were sort of developing it, and we are going to be building this into our Vic variant normalizer pipeline tool that's available publicly as well, and some more stuff coming down the line in the future. Yeah.
Okay, this might be, you might have already covered this and you might have a solution for this and I just missed it.
Sure.
But from my experience, there can be errors in the way things are labeled or inconsistencies across resources that could look like two separate things.
Yep.
You might not see it until you actually get into the data.
Yep.
And I'm sure you're accounting for that, but I'd love to hear a little more about it.
Okay. So the idea here is that with Cat-VRS, there are very few sort of required fields that are in there, but there are structured and highly encouraged optional fields. And the idea is that to the extent that someone can tell us detail about what they're looking at, they put it in there. If they don't know, do not put it in there. And so if, for example, let's say you're a curator on the Civic and they crowdsource a lot of their entries from the literature, right? And someone says, in conclusion, BRAF mutations are associated with blah, right? If the author didn't tell you what they mean by BRAF, you're like, well, okay, they said BRAF, we assume that means a gene. We don't know if they mean the coding sequence, they mean the whole thing, they mean the thing according to, Ensemble 10 years ago or this year or when. So you're just going to tell us the knowledge you know, and hopefully not tell us the knowledge that you're trying, you're having to sort of make up. And we structured it to not force people to do that, right? So one of the problems with like HGVS or something is it had a problem of sort of enforcing via these conventions over precision, which causes problems down the line and damages provenance. We're taking a lot of effort to try to avoid that, and I'd be happy to talk to you more about that. Maybe over wine?
Okay, there seems to be a lot of wine coming. Okay, with this, please let's thank our speaker and all the speakers of this section again.